So in previous class, we have discussed about the importance of differentiation and integration. So why do we need to use integration when there is a need of multiplication of two quantities? When there is a need of multiplication of two parameters and both the parameters are one parameter is varying with respect to another parameter. If one parameter is varying with respect to another parameter, what we have to take? We have to take for a small change in one parameter, what will be the result? What will be the result? And from that result, we have to do the integration. So if we integrate PW, we will get W. So we have to do the integration. So where we have to do the integration? When we multiply two things, and in that one parameter is changing with respect to another one, what we have to do? We have to find the, instead of finding whole work done, instead of finding whole work, we have to find the work for moving small distance. What is the small work? dW means it is not the multiplication of D and W. It is the change in small work. It is the change in small work for moving a small distance by having force F. From this, we have to do the integration. So this is how. So this is how we have to use the integration in our situation. So any doubts on this? Is there any doubts on this one? Okay. Now, so in our situation, we have a charge plus Q, let it be plus Q. And because of this charge, we have an electric field surrounding to this. Electric field surrounding to this. So this electric field is quite big actually. Electric field is usually a big area. So it is not what we think actually. It will be a quite big area only. But the thing is, the significance of electric field. Significance of electric field means where the electric field, the force due to the electric field is significant, is it is near to plus Q. So the area which is near to plus Q only, the electric field is significant. Say example, if you keep your test charge here, let it be point P. Let it be point P. So this charge Q0 won't experience much amount of repulsive force, because so plus Q is here. This plus Q repels this Q0. Usually the test charge, we will take it as plus 1 coulomb only. So in normal situation, this plus Q repels this Q0, but the repulsions won't be that much great because it is somewhat at the large distance from plus Q. But when you bring this Q0 to some point near to plus Q, let it be R. Let it be R. So you are going to bring this Q0 from point P to point R. Point R. You need to move this much distance. So if you move towards plus Q, the repulsion force keep on increases. Every step you take towards plus Q, the more force you will experience. So the distance we are moving is, let it be R. The distance we are moving, let it be R. But say example, Okay, we'll keep like this. The distance between the plus q and plus r. So this distance I take it as r, or else I will take this as r2, and from q to p, this distance, let it be r1. So what I have to do basically, the initial distance is r1. When I step towards plus q, the r1 value keeps on decreasing. Okay, when I reach the point r, the distance will be r2. So the distance I am moving is from r1 to r2. For moving this distance, that is from p to r, for moving this distance I need to do some work. So that work should be force into displacement. But the problem here is I have to do the force against the repulsive force, because this plus q repels it. So whatever work I am doing is against this electric field. So the force is, if F is equal to electrostatic force, if F is equal to electrostatic repulsive force between capital Q and Q0, then I have to do the work against this F. So I just need to put minus, because work is the scalar quantity. Scalar quantity means you don't need to associate any direction. It is the energy we spend. Okay, so we spend the energy against that force. So since it is a scalar quantity, if we spend energy from our body, this Q0 spend energy from this body, so it will be -1. Okay, so basically it against this F, so we need to put minus. So in if you write any scalar quantity, you have to mention whether it is positive or negative. Whether it is positive or negative. So the formula itself, it says that W is equal to minus F into displacement. Minus F into displacement. Is that clear? Is that clear? Now, the thing is, this force value is keep on decreasing with respect to displacement. So this is like this case. This is like this case. The value of F is changing with respect to displacement. So what I am going to take? I am going to take, for a small displacement dr, what is my force? So that is dw. So I have to take minus here. And from that, if I do the integration, I will get the W. So that is equal to minus integral of F dr. Is that clear? F dr. Then the dr value means, so the displacement, the change in displacement. Here you have to put the limit. From where to where? From where to where? From R1 distance to here, the limit you have to put. From where to where? From R1 to R2 you have to bring. So this is how you have to put the integration limit. Okay, is this clear? Okay, now so guys, make a note of this. So this work we can keep it as from P to R. Let it be from P to R. So WP. Now the next thing, so what is WRP is equal to minus integral of R1 to R2 F dr. Okay, F into dr. Okay, So what is this force basically? It is the electrostatic repulsion force. Electrostatic uh, electrostatic repulsive force between Q and Q means capital Q and small q0. So Ashik, can you tell me the formula for that electrostatic repulsive force? So we have a charge Q, and q0 will be somewhere outside. Okay, so we have a distance between them. Since this distance is varying one, I just keep it as r. In our case, the initial distance is r1, the final distance is r2. So anyhow, the distance value keep on changing. So let it be r. So tell me the formula for force. One charge is q, another charge is q0, distance is smaller. What is the formula for F? 1 by 4 pi epsilon 0. Which q? Q or q0? Oh, q into by r square. Fine. Okay, so this is the electrostatic repulsive force. This is the, so to face this force, we need to do some work. Now the thing is, here we have point R, here we have point P, and here we have point R. So we need to move from point P to point R, right? Point P to point R. Okay, right. Now, tell me, if this charge Q0 wants to stay at Q0, wants to stay at P. So we have a big charge Q here. Okay. So now we bring a test charge Q0 here. This Q repels this Q0. Okay. Now assume that if it wants to stay at P, it needs an is it does it need an energy or not? Does it need an energy or not? If it just wants to stay at P, does it need any energy or not? Yes, because it repels. So it pushes outside, it pushes outwards. So if it wants to stay at P itself, it requires an energy. That energy is known as electrostatic potential energy. That energy is the potential energy of Q0 at P. Am I correct? Am I correct or not? Yes, am I correct or not? Now, so let me say it is the potential energy, right? Potential energy is denoted by the letter U. Usually, we will denote potential energy by using letter U. So it will be UP. Again, the same thing. If it just wants to stay at R, the same thing, it needs an energy, that is potential energy at R. Potential energy of Q0 at R. Let it be UR. Now tell me, Pooja, I'm asking you, whether UP or UR, which one is high? In UP and UR, which one is high? At which point the Q0 needs large energy to stay, more energy to stay? At which point this charge Q0 needs more energy to stay? At point P or at point R? So the repulsive force is more at R rather than P because it goes to Q. So at point R, since it faces more repulsive force, it needs more energy, right? So automatically UR is greater than UP. UR is greater than UP. So for an argument's sake, if I say UR is 100 joule, that means you need 100 joule of energy to stay at R, and UP is 50 joule. UP is 50 joule. You just need 50 joule to stay at, so not 50 joule, let it be 30 joule. Okay, 30 joule. UP 30 joule. Okay. Now tell me how much amount of work you need to do to move from P to R. This is my question. If you want to stay at R, you need 100 joule of energy. If you need to stay at P, you need to do 30 joule of energy. Then if you want to move from P to R, how much amount of energy you have to do? How much amount of energy you have to spend? Simple one. From 30 to 100 joule, how much amount of energy you need to do? Simple one. At point R, at point P, if it the electrostatic potential energy is 30 joule. At point R, more electrostatic energy will be required, so let it be 100 joule. So if you want to move from energy at 30 joule to energy at 100 joule, how much amount of work you have to do? How much amount of work you have to spend to move from point P to point R? You don't know. See, this is a 10-floor apartment. Let it be 10-floor apartment. Okay. In that, if you want to reside at third floor, the potential energy what you are having at third floor is 30 joule. The potential energy at 10th floor is 100 joule. Now, if I am asking, if you want to move from third floor to 10th floor, how much amount of work, how much amount of energy you have to spend from your body? That's the question. There will be only one answer, only one possible answer there. If it is 30 joule, if it is 100 joule, means what? How much amount of extra work you have to do? Ashik. $70 joule, that's it. Because you have to do the work against the electrostatic, against the gravitational force. In this case, when you crimp up in the apartment, you have to do the work against the gravitational force. The same way, here you have to do the work against the electrostatic force. So 70 joule of work you have to do. So WRP should be the energy at the electrostatic potential energy at R minus electrostatic potential energy at P. Am I correct or not? So this is the potential energy difference. Am I correct? So what you are finding is the potential energy difference. Potential energy difference between R and P. Okay. Am I correct? Okay. Now instead of potential energy, I'm going to use the potential difference. Electric, if I want to find electric potential difference between R and P. That is, so instead of UR, I'm going to use electric potential difference at R minus electric potential at R minus electric potential at P. So this is the total energy required for Q0. If I want to say what is the electric potential at point R, so UR is the here we can write. Okay. Let VR is the electric potential at point R. So it is not total energy, it is electric potential at point R. And VP is the electric potential at point P. Now tell me, Ashik, I'm asking you, you need to find the potential difference between VR and VP. Okay, VR and VP. So now this test charge is Q0. So what is the value of test charge we have to take? What is the value of test charge you have to take? 1 coulomb. So what we have to do? We have to find the work done for unit positive charge. For 1 coulomb charge, we have to find the work done for 1 coulomb charge. So W divided by Q0, or else UR minus UP divided by Q0, or else integral of minus R1 to R2 F by Q0 dr. And tell me, what is F by VR minus VP? What is F by Q0? Force required for 1 coulomb positive charge is known as force required for 1 coulomb positive charge is known as what? Force experienced by 1 coulomb positive charge. It is force experienced by 1 coulomb positive charge. Electric field intensity. Okay, so VR minus VP is equal to RS. You can simply say VR minus VP is equal to electric field intensity into dr. Or else, if you simply say, if you didn't use integration, dV is equal to dW by Q0, and it is simply minus EdR. Again, I repeat again, dV, the electrostatic potential is equal to dV is equal to minus EdR. Minus EdR. E is equal to electric field intensity, and R is the change in the distance, displacement. So this potential is the electrostatic potential. Now make a note of this. So I will repeat again. Electric potential. Yes. So electric potential at point P. So we have a test charge, we have a source charge plus Q, surrounding to plus Q, there will be an electric field. Now, if you want to find in an electric field, if you want to find electric potential at point P, so there is an electric field surrounding to this plus Q. So in an electric field, if you want to find electric potential at point P, that is work done to bring an unit positive charge from somewhere, from outside to point P. So outside means it will be, we can keep it as, it is from infinite distance, we can make it as infinite distance. So work done to bring an unit positive charge from infinity to point P against electric field. So that's the important thing, against electric field. So dV is equal to minus E dr. If we decode this formula, dV is work done per unit positive charge. So work done is equal to force into displacement. Work done per unit positive charge means force per unit positive charge into displacement. So if you want to find V at point P, if you want to find V at point P, we have to integrate dV. Integrate from where to where? Integrate EdR. Integrate EdR. So integration limit will be from infinity. So base limit should be infinity because we are moving the test charge from infinity to at a distance r. So that is electric potential at point P. A particular point, if you want to define electric potential, work done to keep a unit positive charge against electric field. So that is the electric potential at point P, at particular point. If you want to find in an electric field, if you want to find the potential difference, electric potential difference, then in an electric field, work done to move the same 1 coulomb positive charge from one point to another point against electric field. So work done required to move 1 coulomb positive charge from one point to another point against the electric field is noted as electric potential.